Hi everyone! On the last lecture we saw 4 ways how to construct new rings. But what if we have a subring inside our fixed ring? Then is there any way that we can enlarge it? In fact, yes. If we have an ideal I inside of R, then we can construct a new subring A plus I. A plus I is a subring inside R of elements of the form A plus I, such that A is taken from the subring A and I is an element of the fixed ideal. And we can prove that this is indeed a subring. For this we need to show that it is closed under addition, multiplication, and contains a unit. A plus I is a subring of R. That it is closed under addition should be an easy exercise, and I suggest that you stop video and try to do it. If you have any troubles, you should definitely talk to me during the lecture meeting. Second, it is closed under multiplication. So if we have two elements A plus I inside of A plus I and B plus J, where B is from A and J is from I, we want to check that their product with respect to multiplication in R still belongs to A plus I. So let us open the brackets. I get AB plus IB plus AJ plus IJ. And I note that by the absorption property of the ideal, IB is inside of I, and AJ is inside of I, and IJ is inside of I. Whereas AB is an element of A because A was a subring to begin with. So we have written this product as a sum of two elements, one from A and another from I. So this whole sum lives inside of I. What are some observations that we can make about A, the relation of A and I and A plus I? First, A intersected with I is an ideal inside of A. Because both A and I are closed under addition, this set is also closed under addition. And since I had the absorption property in R, it also has the absorption property in A. Let us check this absorption property. Take I inside A and I, and take A in A, then AI lives in A because A is closed under multiplication, and AI lives in I because I has the absorption property. And this is exactly saying that AI lives in the intersection of A with I. And the second observation is that I is an ideal inside of the subring A plus I. And we can check it in the similar manner. It is clear that I is closed under addition, and as for the absorption property, I satisfies it inside R, and it is a smaller subset of R. So I satisfies the absorption property in here too. So this is also an ideal. Now we should have enough examples of rings and enough ways to construct new rings. But whenever we build new rings, there is always a question, is it something new? So now I would like to remind you the first isomorphism theorem and show two of its corollaries, second and third isomorphism theorems, that will compare certain constructions. Let me recall the first isomorphism theorem. Let's say that phi from R to S is a ring homomorphism. Then the first isomorphism theorem that says that the quotient of R by the ideal, which is the kernel of P, is isomorphic to the image of P inside S. Now let me formulate the second isomorphism theorem. Let's say that we have a ring R and a subring A. As well as an ideal in R. Then the isomorphism that we have is that the quotient of A by A intersected with I, this is naturally isomorphic to A plus I quotient by I. Inside of R mod I. Let us prove this second isomorphism theorem. Our strategy will be to employ the first isomorphism theorem, and so we construct a homomorphism phi from A to A plus I quotient by I, which sends an element A to the which sends the element A to the equivalence class A plus 0, or we can simply write it as A inside of this quotient ring. And in order to employ this theorem, we need to check what the kernel of phi is. The kernel consists of these elements inside A, which are killed by phi, and if we have such an element, it is the same as saying that by definition of phi, A is equal to 0 in the quotient ring, which means that A lives in the ideal. And so the kernel of phi consists of those elements of A which also belong to the ideal. So it lies in A plus I. A intersected with I. And so we have that A mod A intersected with I is isomorphic to the image of phi. And we just note for the last part that the image of phi is the whole ring, because every element A plus I represents the same equivalence class as an element A, because we are modding out by I. And this is in the image. So we conclude that image of phi is A plus I quotient by I, which is the claim that we were interested in. The third isomorphism theorem treats the following situation. Let's have two ideals I and j inside of R, such that I is contained in j. Then the quotient of R mod I by J mod I as abelian groups is isomorphic to the quotient R by J. And before I start proving, I would like to talk about what this means. So I want to make an observation that from group theory, treating I, J, and R as abelian groups, we have that J mod I is an abelian subgroup of R mod I. But being that, we can also prove that this is an ideal. Let us take a representative J inside this subgroup. Let us take a representative, let us take an equivalence class inside this ring. Then the product of these two equivalence classes is JR, and JR lives in J. Therefore, this equivalent class lives inside J mod I. And since J mod I is an ideal, we can quotient out R mod I by this ideal. And the claim is that this quotient is isomorphic to the quotient of R by J, by the bigger ideal J. In a sense, this is a theorem about cancelling out denominators. Let us prove it, and for the proof we use similar logic. We construct a ring homomorphism from R mod I to R mod J, which sends the class of R mod I to the class of R mod J. And we see that phi is well defined, because if we take an element R plus I, then the equivalence class of R plus I is equal to the equivalence class of R, because I, living inside of I, also lives in J, and so we move back by I here to get R. So the images on these two equivalence classes are equal. You can observe from the definition that phi is surjective. And in order to use the first isomorphism theorem, we are going to check what its kernel is. So let's say that phi of R is equal to 0. It happens when R is equal to 0 in R mod J, and by the construction of the quotient ring, it happens when R is in the ideal J, but this is the same as saying that in the ring R mod I, the class of R belongs to J mod I. I will finish the proof up here. Now we know what the kernel of phi is. It consists of all the elements of J mod I. And so by the first isomorphism theorem, R mod J, further quotient out and so by the first isomorphism theorem, R mod I, further quotient out by J mod I, is isomorphic to R mod J. So we clear these denominators and prove the theorem. There is an interesting corollary of the third isomorphism theorem. It says that for a ring R, and for a fixed ideal I inside of R, we have a bijection between ideals of R that contain I and ideals of the quotient ring R mod I. For the proof, we can see that we go from left to right. Let's call this direction alpha. If we have an ideal of R that contains I, then we send it to the ideal J quotient by I. And we observed in preparation of to the third isomorphism theorem that J mod I is an ideal in the quotient ring. And for the other direction, let us take an ideal K inside R mod I. Then we can consider the following flowchart in a sense. R maps to R mod I, and this further surjects onto R mod I mod K. And the kernel of this composite map, let us denote this kernel by J. If this is Q1 and Q2, then J is the kernel of Q2, Q1. So, by the first isomorphism theorem, R quotient by this ideal J is isomorphic to the image of Q2, Q1, which is this whole ring. So these two beasts are isomorphic. But also note that J must note that J must be bigger than I, so J must contain I, because if we have an element in I, then Q2, Q1 of I is equal to Q2 of Q1 of I, but this is 0, so it is Q2 of 0, so this is 0. And by the third isomorphism theorem, down here, R mod J is isomorphic to R mod I, quotient by J mod I. So this map we can view it as a map from R mod I to this quotient ring. And the kernel of this map is exactly J mod I. So K should be equal to J mod I. If I call this pink morphism, if I call this pink homomorphism QR phi, then kernel of phi is J mod I, but we also started from Q2, whose kernel was K. So K is of the form J mod I. And if we have K on the right side, then beta takes K and sends it to J to the left. This is the end of the proof. So the upshot is that you can think of ideals in the quotient ring as of certain kind of ideals in the ring that you started with. Let us consider the following situation. Let's say that we have a ring R with an ideal I, such that the quotient is a field. F will denote the quotient is a field. By this ideology of viewing ideals in F and certain kinds of ideals in R, we can see that there are only two ideals that contain I in R. To be more precise, we recover the picture. Ideals J in R, which contain I, such that I is inside J, is the set is in bijection with the ideals of F. But let us recall from a couple of lectures ago that the only ideals of F, the only ideals of a field are 0 and F itself. So the set of ideals of F is the set of the 0 ideal and the unit ideal. So we see that the only ideal that is bigger than I inside R is R itself. And these ideals are called maximal. Let me first write what these two elements. Let me first point out that under this bijection, 0 corresponds to I, and because 0 is of the form I mod I, and the unit ideal corresponds to R because it is of the form R mod I. And the ideals which possess this property are called maximal. An ideal I of R is called maximal, a maximal ideal if the quotient R mod I is a field. Or equivalently, if the only two ideals that contain I are I itself and the whole ring. And we want that I is a proper ideal. Let us work out some examples. Example 1 of a maximal ideal is the principal ideal generated by X inside the ring of polynomials in one variable with the rational coefficients. We can see this by calculating the quotient G of X mod X. And we can observe that it is isomorphic to Q itself, which is a field. How do we do this so quickly? Recall the proposition from the recall a proposition from the previous lecture, which said that if we have a monic polynomial and x is a monic polynomial of degree 1, then the quotient qx mod x is isomorphic to q taken to the power which is the degree of this polynomial, which is 1. And recall that last lecture I said that this isomorphism is not a ring isomorphism, but in this case it is, because the constant part of polynomials add and multiply in the same way as numbers do, without those cross terms. And more generally, for any ring R, if we quotient out x from the ring of polynomials, then this will be isomorphic to R by the same argument. Example number 2 is the ring generated by two elements x and y in the ring of polynomial in two variables in C with coefficients in C. Let us see what the quotient by this ideal is. C x y mod x y. We can see that it is C by observing that every polynomial is a constant term a plus x times something plus y times something. Or we can apply this reasoning twice, and we take c of x comma y, and we first mod it out by y, and we have that c of x and y is taking polynomials in one variable twice. So we take polynomials in x and polynomials in y, mod out by y. And by this blue remark down here, this is isomorphic to c of x. And then we apply the second the third isomorphism theorem, and say that c of x mod x, which is isomorphic to c, is isomorphic to cx comma y mod y mod x comma y mod y. which is by the third isomorphism theorem, C of xy mod x comma y. And the third example of a maximal ideal, this example is very small. We take the principal ideal generated by 2 inside the integers. Then z mod 2 is the ring consisting of 0 and 1. And you can see that it is a field with 2 elements. Therefore, 2 is a maximal ideal. And finally, there are some examples of ideals which are not maximal. First, the ideal generated by x inside of z x is not maximal because zx mod x is isomorphic to z, which is not a field, or we can also find a proper ideal which contains x. It is the ideal generated by x and 2, which lives in z and is not a unit ideal. Also, ideals xy inside of c x comma y and the ideal generated by one element x inside c of x comma y are not maximal because, for example, we can see that both of them are contained in the ideal x comma y. And also the principal ideal generated by 6 inside z is not maximal because first the quotient z mod 6 is not a field. For example, we can multiply 2 by 3 to get 0. And this never happens in a field, that when we multiply 2 non-zero elements, we get a 0. Or we can say that the ideal generated by 6 is contained inside the ideal generated by 2, because 6 can be written in the form 2 times 3.